Hi. So today what I'm going to do is I'm going to talk about the next section of kinetics, which has to do with what's called the rate law. Okay. So I'm numbering this 14.2. It's called the rate law. And the rate law is based on the following idea, that if we have a reaction, so let's say we have two reactants, A and B, so reactant A and reactant B. And those two reactants form, let's make two products, C and D. Okay. The idea is that the speed of the reaction will follow a particular pattern. And the pattern is the speed of the reaction, which we call the rate, is going to be equal to a constant, which is called the rate constant, times the concentration of the first reactant to some power, which is usually a whole number, like 1 or 2, maybe 0. It is possible for it to be a fraction, but it's usually a whole number. Now, I'm going to use x to represent that whole number. So x is equal to maybe 0 or 1 or 2. But again, it could be a fraction as well. Multiplied by the concentration of the second reactant, B, again, to some value, usually 0, 1, or 2. And those X's and Y's are called collectively, they're called the orders of the reactants. And if it's a 0, we would call it 0 order. If it's 1, it's called first order. And if it's a 2, it's called second order. Okay. So 0, 1, or 2, 0, first or second order. So what that means is the speed of the reaction is actually kind of complicated, right? It depends on a constant. It depends on what the concentration of each reactant is. And it also depends on these orders, these values of X and Y. So just again, as a reminder, K is called the rate constant. Okay. Now, when I say it's constant, it's not constant in the same way that the universal gas constant is a constant. You can use it for any problem. The rate constant is constant for a particular reaction at a particular temperature. The rate constant it's constant for one reaction at one temperature. Okay, so even if you change the temperature, it'll change. If you make it a different reaction, it'll change, okay? Even so, even though it's not constant, meaning you can use it anywhere or any time, it is a useful value, okay? So rate constant times this concentration of A to the X times this concentration of B to the Y, okay? So that's called a rate law. So we can figure out the speed of the reaction if we know those concentrations and if we know the values of X and Y. Part of what we do in this section is figure out how do we get X and Y? How do we determine X and Y so that we can use it? And how do we determine K? Because again, if you don't know all these values, you can't figure out the rate. But that's the sort of puzzle that we put together in kinetics, is figuring out these values. We generally want to know the values of K, X, and then Y, all three of those, so that we can calculate the rate. And as a reminder, remember, we're using this bracket notation. So this is referred to, we call it the concentration of A. And typically, it's in moles per liter. Now, I will point out, this also works for gases. If we're dealing with gases, then the rate is equal to a rate constant times the pressure of gas A to some value times the pressure of gas B to some value. Okay, so that's our background idea for this idea of rate law. Now let me go ahead and pop up a problem here so you can see it. Okay, so the rate of a certain reaction is given by the following rate law. Rate equals K times the concentration of N2 to the third power times the concentration of O3. Use this information to answer the questions below. What is the reaction order in N2? So let's come over to N2. So what we said was the order is the exponent. So the order in N2 is a 3. It's a third order. Okay, so the order is 3, or third order. For O3, there's nothing written up there, so that means it's a 1. So it's first order. So order is 1. The overall reaction, or you just add them together. 3 plus 1 is 4. So that would be good. At a certain concentration of N2 and O3, the initial rate of reaction is 5.0 times 10 to the 3 molarity per second. That's concentration units per time second units. What would the initial rate of the reaction be if the concentration of N2 was halved? Round your answer to 2 significant digits, and then we want the answer in molarity per second. So let's take a look at that one. So what we know, I'm going to just put R for rate. We don't know the value of K really, but we do know the concentration of N2 to the third power has an order of 3, and then O2 has an order of 1. So we do have the rate law. That's called the rate law right there. Okay. Now, what are we told? We're told the initial rate is 5.0 times 10 to the 3 molarity per second. So this is the initial rate. So that's telling us what R is. Okay. And that's going to be equal to K times N2 to the third times O2 to the first power. What would the initial rate be if the concentration of N2 were halved? Now, be careful. Halved, what does that mean? Halved means you go from 1 to a half. You're cutting something in half, right? So now what I can do here is I can write a new rate, I'll just say R2, is going to be equal to K times N2. Now, what I'm doing is I'm cutting this in half. Cutting something in half is dividing by 2, right? So it said, cut the concentration of N2 in half. And then everything else is the same. The concentration of O2 is the same. The rate constant is the same. Okay. Now what I want to do is I want to look at this term here with the N2 over 2. If you cube this term, notice you're going to cube that 2 down there, right? Like if I said, 4 over 2 and I cubed it, that's equal to 4 cubed divided by 2 cubed, right? And that would be, whatever, 4 cubed over 8, right? So really what you're doing there is you're taking this value here and you're changing it so that this term right here is a half as much, but you cube it. So what you get then is K times N2 to the third power over 8 times the concentration of O2, right? See where I got the 8 there? I have the 8 there because 2 cubed is 8. So I brought it out of that, out of the brackets and made it 1/8. So in other words, this right here is going to be 1/8 of what that is. Okay. So if this was 5 times 10 to the 3, which is 5,000, this one would be 5.0 times 10 to the 3. You would just divide it by 8. Okay. So whatever that works out to be, that's 5,000 over 8, right? 5,000 over 8, 625. I rounded it to 2 sig figs. Okay. So there you go. There's that one. Now we have another part of this question. So let's take a look at that one. The other part of this question says the rate of the reaction is measured to be 0.100 molarity per second when N2 is 0.67 and O3 is 1.2. Calculate the value of the rate constant and then round your answer to 2 significant digits. Okay. 0.67 and 1.2, the rate is 0.10. And we want to calculate the value of K. Well, this one's this is what we often call a plug and chug type problem. So let me write it in here. Rate equals K times concentration of N2 to the 3rd power times concentration of O2. Okay. So we're told that rate is 0.100 molarity per second. That's what we're given. We're also told that the concentration of N2 is 0.67 molar, and the concentration of O2, I'm sorry, it's O3. I keep writing O2, it's O3. Doesn't really matter for the purposes of our calculations here, but I'm sorry, it's O3, is 1.2 molar. Okay. And then we want to find the value of the rate constant. Remember, the rate constant is K. So we're trying to figure this out. So let's go through the algebra here. R equals K times concentration of N2 to the 3rd times concentration of O3. We want to find K. So what I'm going to do is I'm going to divide both sides by concentration of N2 cubed. So that's 1, right? So now you have R over concentration of N2 cubed equals K times concentration of O3. We want to find K, so we have one more step. We're going to divide both sides by the concentration of O3. And that will isolate the K. All right, so we have it. So now K, the rate constant, is the rate over concentration of O3 over concentration of N2 cubed. Okay, then we just put our numbers in. So the rate is 0.100, molarity divided by seconds. And then we have N2's, I'm sorry, O3 is 1.2. So 1.2 molar. And then O3, N2 is 0.67. Cube, right? That's a big number, okay? That's a big exponent, cube. So here's what I'm gonna do. I'm gonna take 0.100, divide that by 1.2, and then I'm gonna divide that by 0.67 cubed. And it looks like we get, how many 2 significant digits? So I'm gonna do 0.28. Now look what, they give you the units in here, but I wanna go through it. You have molarity here dividing with molarity. So you have 1 over seconds. That's usually written as S to the -1. So 1 over seconds is written as S to the minus 1. 1 over molar is typically written as M to the minus 1. 1 over molar squared is molarity to the minus 2. And 1 over M cubed is M to the minus 3. So since these molarities cancel, we just have 1 over molar cubed. We just write it as M to the minus 3. It's really just to make it look a little prettier and more official than, 1 over molar cubed second times seconds. It means the same thing, but that's usually how it's done. Okay. So that's the rate constant. So now you know the rate constant and you can use that in other types of calculations. Cool. All right. I want to take a look now at this problem right here. A certain reaction is second order in N2 and second order in H2. Use this information to complete the table below. Round each of your answers to 3 significant digits. So they're telling us that it's second order in N2 and second order in H2. And they want us to, and then they give us the initial rate and they want us to find the rates of reaction under these concentrations. So the idea is here's the concentrations, here's the rate. For these concentrations, what's it going to be? So it's kind of, this is an interesting little arithmetic problem. And that's really what it is. It's really just an arithmetic problem. But it's a common type of one. So let me take a look here. Oops, sorry. Let me show it again to you so you see it. I don't think you saw that. Okay, so a certain reaction is second order in N2, second order in H2. So that means the exponents are 2 and 2. Use this information to complete the table below. Round each of your answers to 3 significant digits. Okay, so these all have 3 significant digits. So they give you these concentrations and the rate. Then they give you these concentrations and ask you for the rate. Then they give you these concentrations and they ask you for the rate. Okay, so it's not, not obvious how you approach this, but like I was just saying, it's really just a math problem, to be honest with you, but it's useful. So we know then that the rate is equal to K times the concentration of N2 to the second times the concentration of H2 to the second. Remember, this is called the rate law. Now, how do I know that's the rate law? Because it said second order in N2 and second order in H2. Okay. Then they give us a table. And they call it the initial rate, which is fine. Okay. Now, what I'm going to do is I'm going to figure out what K is. Okay. Now, here's why I want to do that. If I know what K is and I know what the concentrations are, I can figure out the rate. So in the second part of this, they give us this concentration and this concentration. And then they ask us to find the rate. Okay, then in the third part, 0961, 3.67, and then they want us to find the rate. So here's my logic. This is my approach. And I'm not going to claim this is the only approach. My approach is this. In part 2 and part 3, we know what these concentrations are. So we know these. And we know what the exponents are. So if we know K, we can just put all those numbers in and figure out what their rate is, right? They're asking us for the rate. So in part 1, use the known rate and the known concentrations to find K. It's going to be the same K each time because we're not changing the temperature and it's always the same reaction. I said that at the beginning, right? So if it's the same K, you can just keep using it over and over again. So let's take that step 1. The rate constant, K, is going to be the rate divided by concentration of N2 squared divided by concentration of H2 squared. How did I get that? Well, I took the rate law and I divided by N2 squared and I divided by H2 squared to isolate the rate constant K. So the rate here is 33.0. And then your concentration of N2 for the first one, 0.287. But N2 is squared, so we got to square that. H2 is 1.23. But we got to square that too, right? Because remember, that's squared. You're going to end up with some interesting units here. Let me actually put this in scientific calculator mode. 33.0 divided by 0.287 squared divided by 1.23 squared, and you get 265. Now the units, it looks like one of these will cancel with one of those. So it looks like you got m to the -3 times s to the -1. We don't really need the units to do these calculations, but it's probably a good idea to go through it. How did I get m to the -3, s to the -1? It was kind of like the previous problem. You know, this molarity cancels with one of those. So you still have a molarity here. And then you get a molarity squared. Molarity times molarity squared is molarity cubed. They're in the denominator, so it's to the -1. Seconds is in the denominator, so that's to the -1. So now for part 2, we can find our rate because it's going to be 265 m to the -3, s to the -1. So there's your K times the concentration of N2 squared, so 0.287. Squared times the concentration of H2, which is 0.364 molar squared, right? Yeah, I think I got that right. So I won't go through it, but what you'll end up with is molarity per second, which is the units we want. So 265 times 0.287 squared times 0.364 squared, and you get 2.89. That's what it looks like anyways. Okay, 2.89. Let's try the third one. The third one, and actually I'm just going to check and see we lowered the constant. Yeah, that makes sense. So let's do our same. Again, you get to use the same value of K because the temperature hasn't changed and it's the same reaction. So K, and now we have 0.061. And then 3.67. Now this one jumped up a higher. That's actually a lot higher now. So, you know, if you make one number larger and then you square it, you're going to make the whole thing larger, right? The other one got smaller though. So they might kind of cancel each other out. So times 0.061 squared times 3.67 squared, and you get 13.2. By the way, I'm sorry, this is just 3.67. So 13.2. There's other ways to do this problem, but I'm not going to go through it. Now, again, this is 265 all the way down. Okay. So now that was the approach. I knew the concentrations and the rates, so I was able to find K, use K in the future calculations. Okay, deducing a rate law from the initial reaction rate data. Initial reaction rate data. So you'll see that term a lot, initial. That means that it's being measured early on in the reaction, okay? first few seconds, first milliseconds early on. Some measurements of the initial rate of a certain reaction are given in the table below. So here's a bunch of concentrations for N2. Here's a bunch of concentrations for H2. And here's a bunch of initial rates. So when you have these concentrations here, that's your rate. When you have these concentrations, that's your rate. And when you have these concentrations, that's your rate. Okay? So use this information to write a rate law for the reaction and calculate the value of the rate constant K. Round your answer for the rate constant to 3 significant digits. Okay, so you're going to write the rate law. You may need to use exponents depending on what they come out to be. So let me copy that over here. And so we don't know what the rate law is, but we do know it's K times N2 to some power times H2 to some power. We just don't know what X and Y are, and we don't know what the value of K is. So that's why we have this table of data. They're going to give us 3 different experiments. So 1.24 molar in the first experiment. And then in that same experiment, H2 has a concentration of 1.8. Now remember, during a reaction, the concentrations change. So that's why they call it the initial rate, is because they're saying that's what the initial concentrations are and the initial rate, which is 34.0 molarity divided by seconds. Remember, rate is concentration over time. Okay, so really what's happening here is N2 is reacting with H2 to form something. It doesn't say what it's actually forming. We just know it's forming something. Okay. All right. So we want to find the rate law. So that really means we want to know what these are. That's really telling us that. Okay. So one method for doing this is to take a look and see if there's any patterns. So I'm going to copy down. I'm going to copy down all the data. Okay, so I'm going to look for patterns. And when I say I'm looking for patterns, this is what I mean. If you take a look at the first 2 experiments, only one of the reactants is changing concentration. N2 is the same in both values. It's only H2 that's changing. And H2 is going from 1.8 all the way down to 0.33. So, you know, that change right there is affecting the initial rate. Meaning if I don't change N2, these 2 numbers are the same here. They don't change at all. These do. And so does the rate. So if the rate is changing, it's changing because H2 is changing, right? If you don't change the concentration of something, it's not going to change the rate of the reaction. You have to have a different concentration for the rate to be different. So it appears as though in the first 2 reactions, H2 is affecting how fast the reaction goes. So what I'm going to do is I'm going to do a little arithmetic. I'm going to take R1 over R2. So I'm going to take the rate for the first experiment. That's this one right here, 34.0. And I'm going to divide it by rate 2, which is 6.29. What I'm doing is I'm just making a ratio of how much faster is the first one compared to the second one. So 34 divided by 6.29, and you get about 5.4. Okay, so it looks like reaction 1 is 5.4 times as fast as reaction 2, right? 1 is faster than 2. 34 is greater than 6.29. And now what I'm going to do is I'm going to take the rate law. So I'm going to say K for reaction 1 times 1.24 to the X times 1.80 to the Y. Okay, that's the rate law for experiment 1. And I'm going to divide it by the rate law for experiment 2. So K2. Now keep in mind, K1 and K2 are the same, but I'm just putting the subscript in there so you know that it's for reaction 2. This is also 1.24. And then this is 0.333. Okay. And that ratio we've already determined is 5.40. Why? Because R1 over R2 is 5.40. Now, what's nice about this is that since K is constant, that cancels. K1 is the same as K2. And 1.24 to the X divided by 1.24 to the X, that also cancels. So now you've got 1.80 to the Y divided by 0.333 to the Y, and that's equal to 5.40. Now I'm going to do a little trick here, which is not a real trick. 1.80 to the Y divided by 0.333 to the Y is the same as the ratio to the exponent. So if the base, if you have the same exponent, the numerator divided by the denominator, that ratio can be taken in the parentheses. So 1.8 divided by 0.333. So it's 5.4. 5.40. So 5.40 to the Y is equal to 5.40. Okay. Now there's this is kind of an interesting thing. This is not a math class, but if you remember back when I started introducing these orders, I said they're 0, 1, or 2. Sometimes they're fractions, but they're generally 0, 1, or 2. If you put in 0, a number raised to 0 is 1. So if Y is equal to 0, you would expect it to be 1. If Y is equal to 1, 5.40 raised to 1 is equal to 5.4, right? So what this really essentially means Y equals 1. And now we know over here, we know this is a 1. Okay, so we're getting towards the rate law. That's essentially what we're doing here. We're getting close into the rate law. That's essentially the idea. Okay, now let me go another step here. Now I'm going to look and I'm going to see that it looks like if you take experiment 1 and 3, the N2 is changing concentration, but the H2 is not. So I'm going to take a ratio of R3 over R1 and do the same thing. So I'm essentially going to take R3 over R1. And again, that's going to be K3 times, now we're doing the third one. So N2 is 3.51 to the X times H2 is 1.80 to the Y. And then we're going to divide that by 1, so K1. So 1.24 to the X times 1.80 to the Y. That's a Y. Now, why did I pick 1 and 3? Because again, H2 is not changing, but N2 is. I'm looking for 2 reactions, 2 experiments where one's changing and the other one is not. Okay. Now, why did I put R3 over R1 and not R1 over R3? It doesn't really matter. But what I do is I tend to look at the values of the rate. I tend to want the bigger rate in the top and the smaller rate in the bottom. So that's why I put 3 over 1. It still works if you do 1 over 3, but I did it that way. Okay. Same thing. K is constant. That divides out. 1.8 to the y is constant that divides out. So R3 over R1, again, since it's the same exponent, you can write it as 3.51 over 1.24 to the x. Okay, now let's actually do R3 over R1. It's 272 over 34.0. So 272 over 34.0, and you get 8. Okay, so that means this ratio is equal to 8, right? Because they're both R3 over R2. So now take your 3.51, divide that by 1.24, and you get 2.83. So 2.83 to the x is equal to 8. Okay. So let me just make sure I got that right. 3.51, so 3.51 over 1.24. That's 2.83 to the x. And then let me make sure I'm going to go 272 over 34. And that's 8. Okay. All right. So now what you can do is, I'm not going to go through like the laws of logarithms and stuff like that, but essentially you can start kind of plugging in different values for x. So suppose I make x is equal to 2.83 squared. So 2.83 squared. You get 8. Okay. So like I said, it's either going to be 0, 1, or 2. It's clearly not 1, because if it was 1, 2.83 to the 1 would be 2.83. But I put in a value 2. So remember, your x and y are going to be 0, 1, or 2. Okay. So if you put in a 2, you get 8. So that means it's a 2. And so now you can come over here and you got a 2. Okay. Now you have your rate law. That's the rate law. Now, typically when you write the rate law, you write it as K bracket notation. If the exponent is a 2 or a 3 or a 0, you put it up there. If the exponent is a 1, you don't put anything. Don't put 1 for the exponent. That's considered poor form. Okay. So there you go. There's your rate law. Now, how do we find the value of K? Very simple. We did that in the previous problem. If you know this value and you know this value and you know the exponents and the rate, you can find the rate constant, right? So let's come over here. Okay, so I'm going to do it for the first one. So K1 would be R1 divided by the concentration of N2 squared times the concentration of H2. Okay, that's the algebra we did in the previous problems. So this would be 34.0 divided by 1.24 squared divided by 1.80. So 34 divided by 1.24 squared divided by 1.8, and you get 12.3. Now the units appear to be m to the minus 3 s to the minus 1, because you essentially have molarity over seconds over molarity. Oh, I'm sorry. This is a 2. It's a 2 because you have molarity squared times molarity. So one of these cancels, so you get m to the minus 2 s to the minus 1. Okay, so there's our value for the first one. Let's just try the second one. Okay, I'm going to go ahead and do the second one and see if it's any different. It should be pretty close to the same. And so let's figure that out. Okay, so for the second one, K2 would be R2, which is 6.29, divided by concentration of N2 to the second power, so 1.24 squared, times concentration of H2 is 0.333. Okay, 6.29 divided by 1.24 squared divided by 0.333. I get the same answer, 12.3. Okay, so it looks like you get the same answer whether you do 1, 2, or 3, which kind of makes sense. And there you go. So there's another example of what we call the rate law. Again, for this one, the rate law was R is equal to K times N2 squared times H2. So this is often referred to as the method of initial rates. So if you're trying to look it up online, it's called the method of initial rates. And that is how you determine the rate law and the rate constant using this sort of data right here. Okay. All right, so I'm gonna go ahead and end it at that. There's a couple more from this section that I'll look at in the next lecture. And then we'll keep on going on with this, okay? So take care.